Right, so last time we finished by talking about the formula for the gravitational force, from Newton's universal law of gravitation. And I also mentioned that for spherically symmetric objects, that gravitational force acts as if all of the mass of the object were at the center. So let me just quickly remind you that the gravitational force between two objects can be written as g m1 m2 divided by r squared times r hat. That negative sign indicates that the force is attractive, i.e. it points towards. Notice that r hat points away from one of the masses, so negative r hat points towards one of the masses. And this r is the distance between them. Again, for spherically symmetric objects, it's measured as the distance between the center of masses of those objects. So you might ask the question, and reasonably so, how does this relate to the F equals mg business? And, because we've been using that for the entire quarter, like how do you go from one to the other? So in principle, to calculate the force of gravity from the Earth on an object, so the force of gravity that the Earth applies to some object near the Earth or on the Earth, we need to know three things. So to find force of gravity on Earth, or from Earth rather, which is what that F equals mg business is, we need to know three quantities. We need the mass of the Earth, because the Earth plays a role. We need the mass of the object that the gravitational force is acting on. And we need the distance between the center of masses of the Earth and the object. Now, just to be extra clear, in most instances, the object that we're interested in finding the gravitational force, like a phone, it's not spherically symmetric, but it is sufficiently small that we can treat it as if it's a point mass. So really, we just need to find the distance between the center of the Earth, which is spherically symmetric, and say the center of this object, wherever that is, because the gravitational force isn't going to be significantly different if it's here as opposed to here, or here as opposed to here, right? Just because the distance r is the only thing that will be different depending on the orientation. And that doesn't really change significantly, regardless of the shape of the object, because the object's just so small. So we need to figure out what those things are in relation to an object that's near the surface of the Earth. So just as a quick reminder, just so you have above, we're only interested in the magnitude because we know what direction the force of gravity is from the Earth on an object. It's down, right? So the magnitude would be g. So the force of what do you mean by center of mass?
Was that like a plural or?
Sorry, one more time.
Oh, is like the S after like a plural, like
yes, we need the center of masses of the two objects. Put an apostrophe there. Right, so to find the force of gravity from the Earth on an object, well, we need the mass of the Earth for one of our m's. It doesn't matter which one, but I'm going to put it for the first one. So it would be g times the mass of the Earth times the mass of the object divided by the distance between them. In this case, this r is the distance between the center of mass of the Earth, which is the center of the Earth, and the center of mass of whatever our object is. So how do we get that that the magnitude is equal to mg here? So first, note that for any object that we're trying to find the force of gravity from the Earth on, g times me is always the same for any object on Earth, right? Because it doesn't matter. Doesn't matter what the mass of the object is or the distance from the center of the Earth is. This term will always be there as long as you're trying to find the gravitational force from the Earth on something, right? And so we can just compute that. In particular, it has a name. It's given a symbol. It's called mu sub e, which is the gravitational parameter of the Earth. there's like mu sub s, which might be the gravitational parameter of the sun, and so on. It's just g times the mass. And in particular for the Earth, this is 3.986 times 10 to the 14th meters squared per second cubed, or sorry, meters cubed per second squared. Capital G is Newton's constant. It's just the constant of proportionality that relates, or it's just a constant. It's a number. Go back and look at Wednesday's notes for clarification on that. So that already takes care of the first term, right? Or the first two parts of the gravitational force. And by the way, what we're trying to do is we're just trying to evaluate this, and we're going to hope that it gives us mg, right? So then the question is how far away is an object on the surface of the Earth? Well, on the surface of the Earth, an object is about, well, it's the radius of the Earth. That's how far away they are from the center of the Earth, is r sub e, is the radius of the Earth, away from the center of mass. And that should be sensible, because the center of mass is at the center of the Earth, and the Earth is about a sphere. So the distance that somebody on the surface of the Earth is from the center of the Earth is just the radius of the Earth, right? It's just a sphere. And so that implies that the r that we would plug in here for something near the surface of the Earth, it would be roughly the radius of the Earth. It's not exactly, because, you know, like if something's on like the 8th story of a building, then they're not exactly the radius of the Earth away from the center, right? But it's roughly the radius of the Earth, which is, again, roughly 6.378 times 10 to the 6th meters. So that gives us basically everything we need. Now we just need to talk about that mass. So let's just say that the object has mass m. So for any object of mass m on the surface of the Earth, we can just plug that in, the numbers that we just came up with. The force of gravity, the actual force of gravity, not the mg business, would be, well, it's g times me times m divided by the radius of the Earth squared. But we know what g times me is. We know what the radius of the Earth is. So this would be, you know, g times me. Actually, let me write this as mu sub e. So this is mu sub e divided by the radius of the Earth squared times the mass m, right? I just factored out the mass. And so we can just evaluate that. So we get, this is 3.986 times 10 to the 14th. That was the gravitational parameter, divided by the radius of the Earth. And by the way, the gravitational parameter has units of meters cubed per second squared, and we're about to divide it by meters squared. So the units at the end here will be meters per second squared. And then we're dividing it by the square of the radius. So this would be 6.378 squared times 10 to the 12th, because we're squaring the whole radius. And then this is just multiplied. So that's this part here, and we just multiply it by the mass, the mass of the object. So we can just figure out what number that is. It's just a number. This is 0.098 meters per second squared. Sorry, times 10 to the second. Oops. Meters per second squared times the mass, which is roughly 10 meters per second squared times the mass. So this is g, right? This is where that g comes from. The g comes from the gravitational parameter of the Earth divided by the radius of the Earth squared. Now, this also explains why two objects fall at the same rate, why two objects have the same acceleration. And it's because the formula for the gravitational parameter, for the gravitational acceleration, depends on the mass of the object. So in particular, it doesn't matter what mass this is, it will always have had the same acceleration. Now, I shoved something under the rug. In particular, I said, this is the gravitational accelerate, how you don't explain it, it's just it's just a numerical coincidence, that's all. So everything that I just said only applies for an object on the surface of the Earth, right? Because if you're at a different place, then the value for r is different. But we could account for that. So suppose, and so it is true that the acceleration would be different depending on your height, but we can see how different it is. So let's suppose you throw a cannonball up 10 kilometers. 10 kilometers is about the cruising height of an altitude, or sorry, the cruising altitude of a Boeing 747. So that's about as high as most objects that aren't like in space are going to go, right? Most objects that we would call like on Earth are. So let's see what the gravitational acceleration would be then. So then, yes, it's quite a strong though. Then the radius that we plug in for the gravitational force would actually be the radius of the Earth plus 10 kilometers, right? Because now you're 10 kilometers further away from the center of the Earth than the surface is. So you can go through this whole calculation and you find, again, just replacing RE with RE plus 10 kilometers, is you would find the gravitational force at that height is about 9.77 meters per second squared times the mass. And this is as opposed to the 9.8 that we should have gotten if we wanted to be 100% correct. But the point is this is only 2.3% error if we instead just used 10. And if we had used 9.8, it would have been like a 0.0 or a 0.3% error. But regardless, the error is small, right? So even if you go as far as 10 kilometers up, your gravitational acceleration is still basically the same. So as far as projectile motion is concerned, the acceleration that an object feels is constant. It doesn't it's just mg because it's changing insignificantly at any reasonable height. So what about things that we think of as feeling no gravity, like the International Space Station, right? You might think that the force of gravity on the International Space Station should be like 0, but we can check. So the ISS orbits at about 400 kilometers above the surface of the Earth. So the radius that we would plug in there would be the radius of the Earth plus 400 kilometers. And what we'd find after doing the same calculation again is that the force of gravity on the ISS, or on astronauts on the ISS itself, whatever, would be about 8.68 meters per second squared times the mass. So, it's smaller. It's about 89% of what we would expect. Well, it's about 89% of 9.8 meters per second, but it's 86, or let's just do this right. It's about 87% of 10 meters per second squared. And so this would indicate that the gravitational force on them is like only slightly less, 13% less than what they'd feel on the Earth. So you might, and reasonably so, you would be wondering now, I thought they were in 0G. How are they experiencing gravity if they're in 0G? Like where's the incongruity? So this notion of 0G actually means something that something different than what you might expect. 0G does not mean that you experience no gravity. So it's a misnomer, unfortunately. It actually has to do with all of the other forces besides gravity acting on you. And we can talk about that to some extent. But first, we have to explain free fall. So we're going to try to explain this, and a lot of people I know already know the answer, but not everybody does. So we're going to explain this. So to answer this puzzle, we're going to talk about free fall. So let's look at a simpler scenario. suppose you jump on a trampoline, and while you're just leaving the trampoline, you drop your phone. I know we've all been there. So most of you are probably scrambling to, catch your phone because you don't want it to break and fly off the trampoline, whatever. But if you were instead focusing on what the phone was doing, you might notice something surprising. So here's you on your trampoline, you're on your way up, and then suddenly you drop your phone. So now you're at some higher height. This is a very good trampoline. Some higher height, say VF. But importantly, your phone being over here, it's a Samsung Note 2, so it's like the size of your head, also would just be floating. It would appear to be floating. It's moving up at the same speed as you. So if you dropped it, it would go up as you would go up, and it would come down as you would come down. Now, the reason this happens should be fairly straightforward, right? The phone has the same initial velocity that you do, right? When you're flying up and you just like drop your phone, it's still going up. You didn't like shove it down, it's just still going up at the same rate you are. And it feels the same acceleration that you feel because you both are experiencing gravity, and we just saw that the gravitational acceleration doesn't depend on the mass. So you're going to have the same initial velocity, the same acceleration, and you're starting at the same place. So it'll just appear to just float in front of your eyes as you go up and down, or I suppose in front of your hand. So from your perspective, the phone moves neither up or down. And so in this sense, it's floating. And it's floating in exactly the same sense that astronauts are floating. And so we could say that the phone is in 0G. This notion that things that are just like flying through the air are floating, are in 0G, this is what's called free fall. So free fall is effectively what happens when just gravity is acting on you. Like there's no normal force pushing up on you. There's no, I mean, in real life, there'd be friction here, of course, but there's no normal force pushing up on you. There's no spring force, there's no tension, whatever. It's just gravity. And because it's just gravity, if just gravity is affecting you and just gravity is affecting something else nearby, that something else nearby will appear to just float there. And that's special to gravity because gravity is the only force that only depends on the mass, i.e. it's the only force, sorry, not only depends on the mass, it's the only force whose acceleration doesn't depend on the mass, whose corresponding acceleration doesn't depend on the mass. And so the acceleration that I feel due to gravity will be the same as the acceleration that this pen feels due to gravity, the same that this acceleration that this flashlight feels due to gravity, whatever. And so we can't, so from somebody that's just falling or just being shot up and then going up and then falling back down, they will see everything else that's in the same situation as if it's just floating because they're moving at the same rate as the other things. So now you might say, okay, sure, that's fine for phones on a trampoline, but you might not agree with me that the ISS is falling because, I mean, obviously there's always 400 kilometers up. How could it be that they are falling? Shouldn't they hit the ground? Well, a lot of you guys already know the answer, but I'm going to go over it anyway. But before we can get there, we need to do one more change to this trampoline analogy. So what if we jumped off the trampoline at an angle? So like you jumped off the trampoline, launched yourself off at an angle this way, right? And so both you, and then you drop your phone. Well, both you and the phone are, yeah, you're going to head dive into the ground. Before you do that, before you experience an inconvenient rapid, or what is it, a rapid unplanned disassembly, before you experience that, you drop your phone, and the phone still would appear to be stationary because it has the same initial velocity as you do, it experiences the same acceleration that you do, and it starts off in the same place. So even if you're launching yourself horizontally, the phone will still just move along with you. and it'll appear to float regardless of your horizontal motion. It'll appear to float. So this is to say, whether your motion is up or down, or whether your motion is straight up and straight down, or in a parabola, like projectile, it doesn't matter. Anything that is under the influence of just gravity experiences free fall, i.e. it experiences 0g. But one thing that we should note is that a fired projectile goes further before hitting the ground the faster it was launched. The faster it was launched horizontally. I'm missing an N. I mean, that's obvious, right? If you shoot a baseball at 40 miles an hour, if you shoot a baseball up and to the right at 45 degrees, it'll go much further if you fire it at 100 miles an hour as opposed to 40 miles an hour. That's just common sense, right? Like the object will go further if because it spends the same amount of time in the air, but it'll travel a further distance horizontally. And then we just have to think about the fact that things can't go forever without, I'm trying not to ruin this. The Earth is round. Let me just put it out bluntly. The Earth is round. If you don't believe me, you can leave. So the Earth is round, and so it's not like that. Regardless of how fast you fire something horizontally, it'll always hit the ground eventually, because the Earth curves too. So let's imagine continually increasing the speed of our projectile. So we fire a cannonball, say, and we fire it at ever increasing rates. Projectile, that's how you spell that. So, initially, when you're not firing it very fast, you have your cannonball, and maybe it plops away 100 meters away. Fires out, plops down to the ground. Okay, fine, right? Okay, let's ramp up the speed. So you have now, maybe you fire it so far that it goes like 5 miles away. You fire it so fast, 2,000 meters per second, something really, really fast. So if you fire it so far that it goes so far away, it plops over the horizon. We know the horizon's like, a few miles away. Then the cannonball's trajectory might look something like this. So the horizon would be like as far as you can see. Maybe the horizon's like here. That's about as far as you could see. So when the cannonball goes over the horizon, that means that it crosses the horizon somewhere, right? It goes sufficiently far. Oops. It goes sufficiently far away that it crosses the horizon. But notice, it goes further than what it would have if the Earth was flat. Because if the Earth was flat, it would have crossed, say, there at the horizon. But it goes further than that because the horizon is basically the first place where we start to notice the Earth's curvature. So now imagine you ramp it up to, say, 10,000 miles per hour, right? Now we have to zoom out a little bit more now. Zoom out a little bit more, your cannonballs or your cannon is going to be obviously not to scale. That's a terrible circle. There we go, that's better. Cannon obviously not to scale, but you ramp up your speed to 10,000 miles an hour. Now it travels so fast that the horizon actually falls away pretty fast, and it still hits the ground, but maybe it travels much, much further than what it would have if the Earth were flat. Because the Earth is helping it, it's giving it a little bit more room. And so you can imagine firing it so fast, firing your cannonball so fast, that it just makes it all the way around, because the Earth falls away from the cannonball sufficiently quickly. I hope you're being sarcastic, Ellie. But if you're not, I can't answer that question, honestly. Like, if you're not being sarcastic, then I will answer it honestly. If you are being sarcastic, then, haha. So if you fire it so fast, then this is going to be terrible. Then it can travel all the way around before anything. Okay, so people don't fall off the Earth because, draw a person down here, right? The force of gravity pulls them downwards, right? Force of gravity is towards the center of the Earth. Regardless of where you are, force of gravity is towards the center of the Earth. Yeah. So the point is that if you fire the cannonball fast enough, the Earth will curve away at exactly the rate that the cannonball is dropping. So like if the cannonball would have dropped, say, 1 meter in 1/10 of a second or whatever, then the distance that the cannonball would have covered in 1/10 of a second is how far the cannonball would have to have traveled in order for the Earth to curve away at a meter. Does that mean that people at the bottom of the Earth live I mean, they live upside down relative to us, but we live upside down relative to them. So the point is the speed of the cannonball is sufficiently fast that the Earth curves away at precisely the rate that it would fall down with. And when that happens, we call that an orbit. So let me write this out. So when the Earth's curvature, or when the cannonball is fired sufficiently fast, that the curvature falls out from under the cannonball, curvature of the Earth, at the same rate that the cannonball itself falls down, then we call that an orbit. Or rather, we say the cannonball is orbiting. So obviously, not all orbits are precisely like this. In particular, it's like it could be traveling faster than that, and then the orbit would just look something like this, right? And you could think about why that has to happen if you go faster than that magic value to get a perfectly circular orbit. But generally, an orbit is the situation where you're traveling sufficiently fast that you don't run into the object, the object that's doing the gravitational pulling. So, but this is no different from the projectile motion up here, right? It's just faster. So that is to say, an orbit is just an extreme version of projectile motion. And we already said that objects that are experiencing projectile motion experience free fall. So orbiting objects experience free fall, i.e. 0g. i.e. they feel weightless. Feel weightless. So that's why the astronauts float around in the ISS, even though they still are accelerating towards the Earth at a certain rate, right? It's because when anything is thrown up in the air at any speed, it will have that same acceleration from the Earth. It's just if you're moving so fast, and so you'll always feel weightless, whether you're a baseball that's being thrown or whether you're an astronaut on the ISS. The trick for the ISS is that they get to be weightless forever, because they're not going to hit the Earth eventually. They'll just keep going around it. I mean, eventually it will, but that's due to drag. And so so we qualify that as 0g or no gravity because there's not some point in the future where they're going to crash. That's the only difference. Is this why the moon also orbits the Earth? Yeah. This is why the moon orbits the Earth for the exact same reason. The moon's just moving so fast that rather than falling, it falls away from it. How is this different from if you just drop someone in a random spot in space without any nearby planets to affect their? That's a good question. The answer is that it's not. It's not any different. The experience is exactly the same. And I can actually talk about that in a little bit, but maybe I'll talk about that after lecture, because it's a very, very good question. Like that question gets to very deep physics, but I do have other stuff to talk about. I want to talk about Kepler's laws. So that's why orbits happen. So Kepler's laws are a way of understanding orbits. So I don't know if any of you guys have Curiosity Stream. Maybe today's sponsor is Curiosity Stream. Yeah, he's the Ellipse guy. But Curiosity Stream it's an excellent service, and it has a whole bunch of documentaries. And I love documentaries. That's why I have it. And some of my like favorite YouTubers that I regularly watch, they get money from it, so that's why I subscribe. Anyway, unrelatedly, the point is Curiosity Stream has an excellent documentary on Kepler. Like, it tells the story of his life. It's like a 3-part miniseries. It's really good. I would like, and it explains a lot of the physics that we're going to go over too. But it also kind of makes the story personable. So I actually really like the story of Kepler. It's fascinating. But we're not going to talk about that a whole lot. Just note that Kepler's laws were codified between 1609 and 1619. You know, just over 400 years ago. So I just want to emphasize what a law is. So I want you guys to remember, a law is an empirically derived phenomenon that fits the data. So a law is something like, hey, this thing that I'm observing in nature is doing a thing. I'm going to just write down an equation that thing seems to be following. So like I'm just going to take the data and I'm just going to do like a best fit to it. And whatever that best fit is, that's my law. So that's what Kepler did basically. It was a lot more complicated, especially because they didn't have computers and they didn't have good telescopes. But regardless, he was able to do this, and that's why the story is so remarkable. He was an amazing, an exceptional mathematician. Considering that this was before Newton was a thing, so they didn't know how gravity worked. Just reminding you. So let's talk about Kepler's first law. Kepler's first law was actually not published first, but it's the one that is usually presented first in textbooks. So I'm going to remind you what I'm going to tell you what Kepler's first law is anyway, even though it wasn't the actual first one. So Kepler's first law is the statement that I'm going to copy this word for word if I can. So the paths of bodies trapped in orbits, these are gravitational orbits, of course, form closed ellipses or ellipses with the gravitating body at one of the foci. Hopefully you guys remember your geometry. I don't know, 8th grade, something like that. So by the way, just some more backstory. Kepler got particularly famous because he explained the orbit of of Mars, using this notion of ellipses. Because up until then, the orbit of Mars was not understood, how Mars moved through the solar system. They just couldn't explain it. And so by introducing this notion of ellipses, Kepler was able to explain it. And that's what made him particularly famous. So now you guys need to remember your elliptical geometry. So let's just briefly go over that. So the geometry of an ellipse is like a squashed circle. That's a terrible ellipse. I'm so sorry. That's a pretty good ellipse, but it's not closed. It'll have to do. So the focus of an ellipse, or rather the foci of the ellipse, are 2 special places inside an ellipse along the semi-major axis. So you would have one here and maybe one here. You also have your semi-minor axis. So here we have a focus. Here we have another focus. The plural of focus is foci. Foci is one of the focuses. So it's one foci is plural of focus rather. So this distance here is called A, which is the semi-major axis. Semi meaning half, major meaning big. And then this distance here is often called B. It is the semi-minor axis. Half of the small axis. Yeah, it's all about the epicycles. And then there's one more, so there's A and B. Those tell you how big and how squashed the ellipse is. And in fact, you can actually relate the squashedness of the ellipse just to the semi-major axis and another number. In particular, this distance, the distance from one of the foci to the center of the ellipse, this has a formula for it. That distance is E times A. Here, E is called the eccentricity of the ellipse. And in particular, E is equal to 0 when the ellipse is a circle. So, and that kind of makes sense because the distance between the foci, when the foci are at the same place, when they're at the center of the ellipse, that means that it's not stretched out. By the way, the reason why these ellipses are necessary, or why these foci are necessary, is because the distance, the sum of the distance from the foci to any point on the ellipse is the same. So the sum of this distance is equal to, say, the sum of this distance. And so you can imagine that if the foci are in the same place, then that means that the distance from that place to anywhere on the ellipse is fixed. And that just makes it a circle, right? So now we have to give, so the point is if we're talking about, say, the sun, if the sun is at one of the foci, that's the gravitating body, then one of the planets would orbit in the focus, or would orbit in the ellipse around that focus. So the sun would be at one of the foci. So regarding solar orbits, there's a name for when a planet is at the closest point to the sun. So the aphelion, the physical significance, not a whole lot really, at least not as far as we care about. The aphelion of an orbit is the point in the orbit furthest from the sun. So if the sun was over here, then this would be the aphelion. Perihelion is the point in the orbit closest. So over here would be the perihelion. It's just two names, because back in the 1600s and 1700s, people were just giving names to things because they didn't understand it. Now we would give it a better name if we could, but tradition. So we can actually describe we can describe the shape of the ellipse mathematically actually relatively easily. So let's draw another ellipse. Oh, it's so bad. It's like an egg. There we go, that's better. Yeah, apoapsis and periapsis are the same thing, but for Earth, I believe. It's either for Earth or for just general object. No, perigee and apogee is for the Earth. Apoapsis and periapsis are just the furthest and closest points away from just a generic orbiting or a generic gravitating center. That's all. So all perigees and perihelions are periapses. Yes, precisely. Yeah, precisely. KSB. My God, KSB is the best game for learning orbital mechanics. Like I spent way too much time playing that game. I had to uninstall it because I was, anyway, great game, 100% would recommend. Right, so if the sun is here at one of the foci, and here's our semi-major axis, then in a point on that ellipse can be described by a distance from the focus and an angle. And the relationship between that distance and the angle can be described mathematically. So r of theta, so you input the angle and you get a distance out, would be equal to a times 1 minus e squared divided by 1 minus e cosine theta. So it depends on both the semi-major axis, the length, and the eccentricity. And so if you know theta, then you can just, and you know a and e, then you can find out how far away you are from the sun. And so you can actually just check. If you plug in e equals 0 here, you would just get that r, this is a check that e equals 0 implies a circle. It implies that r of theta is just a, i.e. the distance from the focus is constant, which is just what it means for something to be moving in a circle. The distance from some fixed point is constant, right? So great. So now we know that objects that are orbiting about a gravitating source move in ellipses. That's Kepler's first law. It was a big deal at the time. They were talking epicycles and epicycles and semi-hemi epicycles and all sorts of funky things. And then Kepler's just like, hey, what about ellipses though? Anyway, downside is this isn't quite true, right? It's pretty good, but we know that gravity is a two-way force, right? The sun pulls on the planets, but the planets also pull on the sun. So it's not like the sun is sitting there fixed in place and all the planets are orbiting around it. The planets are also making the sun move a little bit. So in particular, the correct way to phrase this would be to say that the center of mass of the two bodies is at one of the foci, and then both of those bodies orbit in an ellipse around that focus. Now, for the purposes of the Earth and the sun, like the center of mass of the Earth-Sun system is like 100 kilometers away from the center of the sun, and the sun is like 100,000 kilometers across. So it's basically still within the sun. But, you know, for Jupiter and the sun, Jupiter is much farther away and much heavier. The center of mass of the Jupiter-Sun system is like just outside the edge of the surface of the sun. What makes each of the planets have gravity and what makes it stronger or weaker on different planets? Oh, well, so each of the planets have gravity because of Newton's universal law of gravitation, right? If the mass is bigger, then the gravitational force is stronger. And also, it also depends on the size of the planet. If the mass is big but the radius is small, then the gravitational acceleration near the surface of the planet will be big. And so you could do this for the moon. You could plug in the mass of the moon and the radius of the moon, and you'd get a different gravitational acceleration, about 1/6 that you would experience on Earth. So what about Kepler's second law? Kepler's second law seems less intuitive, and indeed, I would say it is. So this is the statement that a line joining the sun and an orbiting planet sweeps out equal areas in equal times. It's out equal areas during equal intervals of time. So as written, you might think that that's just obvious, but think about it for a second. If we have a really extreme ellipse, and the sun is like here, right? That's saying that if you have the Earth here and then the Earth here, this area, call it A1, would the time that it would take to go from one part of those to the other part, say this is delta T1, that would take the same amount of time that the Earth would sweep out this distance, A2. So Kepler's second law says that if A1 is equal to A2, and these are just like areas, by the way, like just, you know, units of meters squared, then delta T1 is equal to delta T2. Now this might be like, okay, why do we care? But think about it for a moment. That means that an object traveling, an object that's closer to the sun has to sweep out a bigger angle in a given amount of time because the distance is shorter, so it has to sweep out a bigger angle to have the same area. So this implies that, say, the average speed at during duration T2 is bigger than the average speed during duration 1, which is to say that objects move faster near perihelion than aphelion. Which this is just reiterating, objects that are like at the closer points in an object's orbit, closer point to the sun, say, that object is moving faster. And this kind of makes some amount of intuitive sense, right? So on the way from aphelion, say from here to here, the object is falling towards the sun, right? It's missing a little bit because it's moving that way and it's trying to be pulled towards it, but it can't because it has some speed. But it is falling towards it. And so in that sense, it's going to pick up speed as it falls towards the sun. Whereas on the return trip, the object is going up and it's moving away from the sun. And so it's going to lose speed. Oops. So it kind of makes sense that it would be faster when it's closer and slower when it's further away. Now the final of Kepler's laws is Kepler's third law. And we're going to do some mathematical details on this on Wednesday, probably, but I'm just going over the ideas here. Kepler's third law is the most surprising, perhaps, which is that the square of the orbital period of an orbiting body orbital period is how long it takes to make one full orbit, is directly proportional to the cube of its semi-major axis. That is not how you spell semi-major. Now that seems kind of arcane, and it really is. But this is just to say mathematically, and this is all for a single gravitating source. So if we're just talking about the sun, then this would be true for planets around the sun. If we were talking about the Earth, then it would be true for things orbiting the Earth. So mathematically, this says that t, which is the orbital period, the square of t, is proportional to the cube of the semi-major axis. Or put another way, it's that a cubed divided by t squared is proportional to 1, which is that a cubed divided by t squared is a constant. If something's proportional to 1, it just means it's a constant. And so this means that if you take any orbital period of any planet going around the sun, or if you take the orbital period of any planet going around the sun, square it, and then use that as the denominator for, let me rephrase, if you cube the semi-major axis of any planet that orbits the sun and divide it by the square of the period, you'll get the same number regardless of which planet you choose. And this is super useful because it means that we can figure out how far away an object is just by knowing how long it takes to go around the sun. Because, for example, we know how far away the Earth is from the sun, and we know how long it takes for the Earth to go around the sun. So if we, and because a cubed divided by t squared is the same constant for any planet, if we just know the constant, which we can find by dividing a cubed by t squared for, say, the Earth, then we can find it for any other planet, assuming we know how long it takes for it to go around the sun. We can figure out how far away it is from the sun. And you could do this, for the Earth. Like if you know how fast the moon goes around the Earth, and you know how far away the moon is from the Earth, and you know how long a satellite takes to go around the Earth, then you can figure out how far away that satellite is, or vice versa. If you know how far away the satellite is, you can figure out how long it takes to go around, and so on. So the constant is different for different gravitating centers. So for the sun, it would depend on the mass of the sun. So that constant depends explicitly on the mass of the sun. For the Earth, that constant depends explicitly on the mass of the Earth. So the constant is the same for any two objects that are orbiting the same central object. Now, in the lecture, or in the example, or sorry, in the lecture notes, I actually go over an example for a geostationary satellite, but we don't have time to do that. So I'll instead leave it to you guys to take a look at that example. But I just want to mention that this result that we derived here can be derivable, like you can derive it from Newton's universal law of gravitation and then Newton's three laws. But Kepler didn't know any of that, and that's what made Kepler so remarkable. Like that's why he was clearly very, very smart. He didn't have the gravitational he didn't know how gravity worked. He had no idea. He just knew that planets moved, and yet he came up with this result, which is derivable from Newton's laws, i.e., it is his prediction, his experimental laws were just correct without actually knowing where they come from. And so just to say this, all of these laws in principle can be derived from Newton's universal law of gravitation. They just weren't because, Kepler's a badass. Anyway, so that's the end of lecture for today. We'll continue on Wednesday.